Alright guys, so in the second video this week, we're going to talk about geometric series. So to start this off, what I want to do is just give you a brief little reminder of what a series is. So a series, as hopefully you recall from last week, we usually denote by S little n, is just the sum of the first n terms of a sequence. So what exactly does that mean? So let's say we've got a sequence. Let's say we've got the sequence Tn is, say, 1, 2, 4, 8, right? So this is a sequence where every time we multiply by 2, so this would be a geometric sequence, right? So every time we multiply by 2 to get the next number. So the geometric series of this sequence would be, say, S1, right? S1 would be the sum of the first term, right? So that's just 1. S2 would be the sum of the first two terms, so 1 plus 2 is equal to 3. S3 would be 1 plus 2 plus 4, right, which is 7, etc., 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 until we got up to Sn, which would be 1 plus 2 plus 4 plus ... up until Tn. So that's the idea of what a series is, and in particular, a geometric series, right, is the series of a geometric sequence. So it's the series of a geometric sequence. So that means the sum of the first n terms of a geometric sequence. Okay, so that's not too complicated of an idea. But what I want to do now is just like we did for arithmetic series, right? Remember how we came up with an equation for arithmetic series that told us what Sn would be for any n. So what the sum of the first n terms of any arithmetic series would be for any n. So what I'd like to do is give you something similar for a geometric series. So instead of going through like a derivation like I did for arithmetic series, I think it would be better in this case just to give you what the equation is. But if this kind of worries you or anything, what I'd really encourage you to do is in class just get my attention, and I'd be more than happy to show you how you can actually get this. But it just takes a little bit of time and probably isn't really worth it this week. So what I want to do now is just write down an equation for the sum of the first n terms of a geometric sequence, so for a geometric series. So for any geometric series, right, so the geometric series Sn, we have this nice little equation which looks like this. So it's a times 1 minus r to the power of n divided by 1 minus r. So for a given geometric sequence, right, we would know what r is. That's the common ratio, and we would know what a is. That's the first term of the sequence. And we would be able to work this out in terms of n. And then if we were given, say, a particular Sn that we were looking for, like S10 or S20 or S3 or whatever, we could then plug that value of n in and work out what the geometric series would work out to. So this right here is a really, really important formula, and it's the one we're going to have to come back to over and over again in the exercise for this part. So what I want to do now is basically just work a couple of examples using this geometric series, and then I've got one more little thing to tell you a little bit later on, and then hopefully we'll be done. Okay, so let's, for right now, work an example. So what I want to do first of all is work one example where I give you the sequence, and then we apply this formula in order to work out what the geometric series for some number of n would be. Okay, so let's give you the sequence. Okay, so it has to be geometric, right? So we have to have a common ratio. So I'm going to give you the sequence, let's see, 1, 3, 9, 27, etc. And what I'd like us to try to work out would be, let's see, let's work out what S5 is. Okay, well, we know, right, this is a geometric sequence because each term is the previous term multiplied by 3. So I can use this equation up here to work out what S5 is. So Sn is this thing up here, so let's just plug 5 in for n. So S5 is A, right, times 1 minus r to the power of 5 divided by 1 minus r. So now all we need to do is work out what r is and work out what a is, plug those numbers in, and we'll be ready to go. Okay, so this bit's pretty easy, right? Okay, so a, remember, a is the first term, and this is equal to, in this case, this number 1 here. So a is equal to 1. So the common ratio, right, is this number here, and that's called r, so r is equal to 3. So I can plug these, right, back into this equation and work out what S5 is. And that's a fairly simple thing to do, so let's do that. S5 is equal to A was 1, right, 1 times 1 minus r was 3 to the power of 5, divided by 1 minus 3. And now I can plug all of this into a calculator and work this out. Let's simplify a little bit first, just because I don't really like calculators that much, as you guys know. So this is 1 times, so I can just get rid of that bit, because 1 times anything is that number back again. So that's 1 minus 3 to the power of 5 divided by 1 minus 3 is negative 2. So let's work this out. So I said 1 minus 3 to the power of 5. That was the numerator, right? And then divided by negative 2. That's 121. So this whole thing works out to 121. Now you could go back and do the same thing for some other value of n, right, and work out what it would be. So rather than do that, what I'd like to do is go back in and just put n in and then try to simplify that. We won't actually be able to simplify it very much, but let's just do it just for practice. Okay, so the next question is, what's Sn? So remember, this just means the series for any value of n, right? So we're not going to put any value in there, we're just going to leave it as it is. So Sn, we said, was A times 1 minus r to the power of n divided by 1 minus r, and we also said A was equal to 1 and r was equal to 3. Right, so we can simplify this a little bit. Let's go 1 times 1 minus r to the power of n and divided by 1 minus 3. So again, get rid of that. That's just minus 2. 1 minus, when I forgot to plug my value of r in there, so that's 3 to the power of n. 1 minus 3 to the power of n divided by negative 2. So I could leave it like that, or I could also get rid of the minus sign there and say this is 1/2, right, 3 to the power of n minus 1. Now, don't really worry about that too much. If you can't see that, that's fine. You can leave it like that. And that would be basically as simplified as we could get for this Sn. Okay. So now let's try to do something slightly different. So let's try to work out an example where instead of giving the actual sequence, where we give you an equation or the functional definition of our sequence, and try to use that to work out what this series would be. So e.g., so let's see, what was this equation again? Okay, so let's start out with Tn, right, is equal to, let's make it 4 times 3 to the power of n minus 1. Right, so we're not actually going to worry about writing this sequence out, but there's enough information here for us to be able to work out what, say, let's do S4. So we're going to find the sum of the first 4 terms of the sequence without actually writing out what the sequence would be. Right, so we know S4, again using this equation up here, S4 should be equal to A times 1 minus r to the power of 4 divided by 1 minus r. So let's write that down here. S4 is equal to A times 1 minus r to the power of n, so that's r to the power of 4, divided by 1 minus r. Okay, so now all we need to do is try to work out exactly what A and r are. So A, well, first of all, let's compare this with our general equation for a geometric sequence. Remember, for a geometric sequence, we had this equation that looked like this. Tn was equal to A times r to the power of n minus 1. So let's now compare this equation here with this equation here. So what number is raised to the power of n minus 1? Well, that's 3. So that, right, r must be equal to 3. Okay? And a must be the number that's multiplying it. So a has to be equal to 4. So the first term of our sequence would actually be 4. Then the second term would be 12, 48, 12, 36, etc., etc. But we don't actually need to work out those terms. We can just plug these numbers into this equation and work out what the sum of the first 4 terms would be. So S4 would be A was 4 times 1 minus R was 3. So that's 3 to the power of 4 divided by 1 minus 3. So we can simplify this now. Let's simplify a little bit first. So that's 4 times 1 minus 3 to the power of 4. 1 minus 3 is negative 2. So what I'm actually going to do is divide 4 by negative 2 to start with to give me negative 2 times 1 minus 3 to the power of 4. So let's work this out. 1 minus 3 to the power of 4. So that's working out that bit in the brackets first, and then times negative 2. Oops, that's not what I did. Negative 80 times negative 2 would be 160. So that's 160. Okay, so again, not too terribly difficult. So now what I want to do is think about something slightly different. So when we have a geometric series, a geometric sequence, right, we don't always have to have the sequence where it gets bigger and bigger, right? It's possible for our value of r to be less than 1. So let's do an example like that. So where that would mean that each number, if each number is going to be multiplied by this number, that would mean the sequence gets smaller and smaller and smaller. Okay. So let's work out an example like that. So let's do the example where, let's say, I've got Tn is equal to 9 times 0.5 to the power of n minus 1. Okay. So what would this sequence actually look like? Well, the first term, when n is equal to 1, so that would give us T1 is equal to 9 times 0.5 to the power of 1 minus 1. So this whole thing is just going to be 1, right? Because this is going to be 0, and any number to the power of 0 is 1. So that first term is 9. T2 is equal to 9 times 0.5 to the power of 2 minus 1. 2 minus 1 is 1. 0.5 to the power of 1 is just 0.5. So that's 9 times 0.5, which is, let's see, 4.5. T3, right? So each time it's just going to be multiplied by 0.5 again. So 4.5 times 0.5 would be 2.25. You could also plug it into the equation and work it out, but we don't actually need to every time. T4 be 1.125, etc., etc., etc. So basically what we're going to do is we're going to have a sequence that looks like this. Okay, so the first term was 9, the second term is 4.5, the third term is 2.25, third term is 1.125, right? And the numbers are going to keep getting smaller and smaller and smaller. So if you guys can remember all the way back a few weeks ago to when we talked about the logistic equation, right? We talked about how some sequences converge and some sequences diverge. This would be an example of a converging sequence. Right? And in particular, as n gets bigger and bigger and bigger and bigger, this number would get smaller and smaller and smaller, and we would say that it converges to 0. Or in that funny language that we used earlier, we would say as n approaches infinity, right? So as n gets bigger and bigger and bigger, Tn approaches 0. So basically Tn gets smaller and smaller and smaller until eventually it's really, really close to 0. So geometric series is, as long as this multiplying factor is less than 1, they actually tend to converge to 0. They will always converge to 0. So this actually gives us, well, what I want to say is it allows us to work out what the infinite series, and this is kind of a funny concept, but what I want to talk about now is infinite series. So what exactly does that mean? So we would write this as S infinity, right? So what this really means is that would be, say, T1 plus T2 plus T3 plus, and instead of stopping at some number n, you would just keep on adding it and adding it and adding it and adding it, and would never actually stop. Okay, so there's something kind of special about the series of a converging sequence when it converges to 0, because oftentimes you can actually work out that it doesn't actually matter. You can keep on adding and adding and adding and adding, but you actually still get a finite number that this thing adds up to. So enough talk. Let's just go ahead and give you an equation to work with. So, like I say, sometimes this S infinity here actually works out to be just a regular number. So you can keep on adding it up, and you still just get a regular number at the other end. So, in particular, for geometric series, right, when the magnitude of r is less than 1, and that just means that r is somewhere between, it's less than 1, right, and greater than -1. So on a number line, you can think of it like this, okay? So r, let's see if I've got -2, -1, 0, 1, 2, right? That means that r lives in this region, right, between -1 and 1. That's all we're just trying to say here. Okay, so when that's the case, right, then that means that your sequence is going to get smaller and smaller and smaller because you keep on multiplying by something that's less than 1, right? So your sequence is going to get smaller and smaller and smaller, and you can actually work out what this S infinity is. So remember, we said Sn is equal to A times 1 minus r to the power of n divided by 1 minus r. Now, if r, right, if the magnitude of r is less than 1, if r is less than 1, then like I say, r to the power of n is going to keep getting smaller and smaller and smaller, right? So if the magnitude of r is less than 1, then r to the n, right, as n gets bigger and bigger and bigger, so as r approaches infinity, Rn actually approaches 0. Right? So if we were to take this to the extreme, right? So let's say this is S infinity. So if we take n all the way to infinity, so it just keeps on going and getting bigger and bigger and bigger, right? This whole thing would be equal to A times 1 minus, well, r to the power of n, we said, as n approaches infinity, r to the n approaches 0. This thing is actually just going to be 0. Okay? A times 1 minus 0 divided by 1 minus r. 1 minus 0 is just 1, and a times 1 is a. So this thing simplifies to be a divided by 1 minus r. So this is actually a really neat little trick. And this is an important equation, so I'm going to write it again. S infinity is equal to a divided by 1 minus r. And like I say, this is a really, really neat little trick. So what this is saying, right, is that if we have, this is for r less than 1. So if we have r less than 1, right, we can take a geometric series and we can add up an infinite number of terms and get just a really regular number. So to show you how this works, let's go ahead and work out what this example up here would be. So remember, we said Tn is equal to 9 times 0.5 to the power of n minus 1. So e.g., okay, Tn is equal to 9 times 0.5 to the power of n minus 1, right? So a is 9, and r is 0.5. Now on that number line, right, r of 0.5 is right there, right? So it's definitely within that region. It's less than 1. It's greater than -1. So it's inside that region. So that means that we can apply this equation here. So S infinity, right? So the sum of an infinite number of terms of the sequence is actually equal to a divided by 1 minus r. So that's 9 divided by 1 minus r was 0.5. So this is 9 divided by 0.5, and that's actually equal to 18. So like I say, if you think about that, that's a really, really interesting result, right? So what we said is we're taking this sequence up here, right? 9, 4.5, 2.25, 1.125. You keep on, if this thing keeps on going, you can add up all the numbers in that sequence and just keep on going and going and going. And if you add them all up, right, an infinite number of terms, you get this number here, 18, right? So the sum of an infinite number of terms of the sequence is just exactly 18. Okay. So I think I've been going on for more than long enough today, so I think that's enough for now, but I'll see you guys in class.